Okay, so good afternoon, everybody. So last time, guys, I started to explain interrupts. Again, this is one of the most important topics. I hope you understand very well. I will do my best. I want you to help me, focus with me. If you have any question, just raise your hand. I want you to understand it. So here, I want to, last time I started to explain interrupts, okay? And I made it very clear. Without interrupts, you cannot make big programs. I'm not gonna buy everything I taught in chapter 3 was like toy examples, right? Why? Because I'm not gonna buy a microcontroller to make like flashing and that's it. Microcontroller is busy all the time. I'm not gonna do that. Microcontroller can do a lot of things, okay, at the same time. That's why interrupts is very important, okay? So quickly, the way I explained it last time, guys, I told you the idea of the interrupt is there should be an event, okay? And because of this event, microcontroller is gonna suspend the program. So if this is your program, I'm expecting after this move, microcontroller come here, after this one come here, after this one come here. That's not totally true. Microcontroller, after finishing the instruction, microcontroller is gonna go to the next one if there is no interrupt. If there is interrupt, it's gonna go serve the interrupt and come back. You got what I'm saying? So what do you mean by go and come back? I mean every interrupt has a subroutine. So after executing the hardware, after executing every instruction, the hardware automatically is gonna take microcontroller to next one if there are no interrupts, or is gonna jump to the subroutine here and then come back to here. Is that okay? You don't need to call. So it's like when you call a function. However, there is a big difference. When you call a function, I have to write a command to call a function. But this time you don't write a command to call a function. This is done by the hardware. You got what I'm saying? You go execute a subroutine and come back. And that's what we mean by the word. You should also be familiar with the word serve. Serve is an interrupt. What serve is an interrupt means? So serve is an interrupt means execute the subroutine. That's it. If I execute the subroutine, I serve the interrupt. Is that okay? So you should be familiar with this term. One more thing I want to explain also. You are telling us an event. So the whole story starts with an event. The whole story, that's true. So what do you mean by event? Okay, I'm going to tell you what I mean by event. Actually, it depends the definition of event. It depends on the interrupt source. Okay, because last time I told you, I'm going to give you more details for sure. Last time I told you we have many sources of interrupts. All of these are sources for interrupts. And every source has a different definition to the word event. So event here is not similar to the event here, is not similar to the event here, it's not similar to the event here, and so on. Okay. So for now, I'm gonna give you definition for event in two interrupts. The first interrupt, we call it IRQ interrupt. And the idea of this interrupt is that we have an external pin. This is a microcontroller. Every time there is a falling edge on this pin, you trigger interrupt. Okay. So so here in this case, what do you mean by event in this case? Event in this case is a falling edge. Okay, signal. This signal is coming from a sensor, it's coming from fire alarm, coming from somewhere, device coming from somewhere. Okay, it depends on your application, as I'm going to explain later in details. So the word event here means a falling edge. So every time there is a falling edge coming from a sensor or from somewhere, this is what I mean by event. Okay, so this falling edge is gonna request interrupt. Okay, and then in order to serve the interrupt, there is a subroutine for IRQ. So I have to execute the subroutine of IRQ. So here I just give a definition to what I mean by event in this case. Let's have another case. Okay, but again, the definition of event is different from one case to another. For now, I'm gonna give you two cases for now. Just to understand what I mean by event for now. But again, event, it depends on the source itself. The second one, we call it RTI, real timer interrupt. So this is actually interrupt coming from a timer. You have a timer. So you have a timer, and then you are gonna ask the timer, please timer, interrupt me every 1 millisecond. Interrupt me everyone. So you need to set up, yeah, for sure. That's what I'm gonna explain today, hopefully today or next time. You need to do some code you need to set up the time of the timer, okay? So that the timer is gonna make periodic interrupts every certain time, okay? So that means every 1 millisecond you should expect interrupt every 1 millisecond. So here, what you mean by event here? Event mean time out. So event here means time out. It means it's 1 millisecond. That's the meaning of event here. Okay, guys. So every time out, the timer is gonna request interrupt, and we are gonna serve the interrupt by executing the subroutine. And then, as you will see later, write in the subroutine whatever you want to do. Right? For example, if this signal coming from fire alarm is telling you there is a fire, then you need what action you want to take. The action you want to take, write it in the subroutine. That's it. Very simple. You got what I'm saying? Same thing here. I'm going to have interrupts every 1 millisecond. What action you want to take, write it in the subroutine. What do you want to do every 1 millisecond? Write it in the subroutine. Okay. So anyway, I just want to define here the idea of what I mean by event. For sure, I'm going to give you more details. For sure, that's what I'm going to do. But again, the most important thing, guys, now my program is not going to go this way as we expect, or as we without interrupts. That's true. Without interrupts, if there are no interrupts, so my program is going to come this way. Okay. However, in reality, as I told you, after executing so I'm not going to suspend if I'm executing an instruction right now, okay, and interrupt came, I'm not going to go and serve the interrupt immediately. I'm not going to do that. After, I'm going to check for interrupts after I finish executing every instruction. Is that okay? So after executing every instruction, okay, either I'm going to go next instruction or I go for interrupt. Okay, so this happens automatically. You don't need to do anything by the hardware. Okay. And so this is what we now. Also, I explained last time. I give you several examples. I don't want to repeat what I said last time, but I think I give you very good example easy to understand that. I give you very good example. If you can understand, you will understand. If you can understand this slide, and next one, you will understand what I mean by interrupts or how it is useful. So here I explain, if I want to do two things at the same time, I have two tasks. I want to do flashing, as you see here. I want to do flashing. Also, I need the code for the keypad. So I want to do two tasks at the same time. Without interrupts, simply, you can't do that without interrupts. You can't. Okay? So, because you can only do one task at a time. Okay? So, but with interrupts, what I can do, I can put here one task in the main program. I can put another task in one interrupt subroutine. That's why from now on, our program will look like something like that. Our program, what we are doing right now, including tomorrow's step, from the beginning of the semester until tomorrow's step, all what we did, we just wrote one task. Okay, this task was in the main program. That's what we have done so far, right? So you have here. So after we learn interrupts, this is how your program will look like. Number one, you have the main program. The main program here has the main function, or the main here, and also it has subroutines. All the subroutines are okay. All of that we call it the main program. Is that okay? And now here you do one task here. Okay. And then we have a number of interrupt subroutines. Okay. So I can do here another task. I can do here another task. I can do here another task, and so on. So by this way, you can do several tasks at the same time. And the idea is that here I'm gonna suspend this task to go execute the subroutine and come back. Suspend this task, do this one and come back. Suspend this task, go and come back. Suspend this task, go and come back. But the main idea here, because I do it very quickly, you are gonna feel like everything is running at the same time. It's smoothly. You are not gonna feel like anything is suspended. You know what I'm saying? This is for sure. If you have a number one, if you write your program correctly or in a good way, okay, Number two, if you have a reasonable number of interrupts, because as I told you, I don't do magic. Okay, what I want to say is that if we have limited resources, so if I use too many interrupts, you will start to feel the program is frozen somehow, okay? Because you are going to start to feel the suspension. The program is suspended here. You got what I'm saying? This is one thing. Another thing, and this is very important. I'm sure many students make this mistake. Please don't do it, okay? Another thing here, as I'm going to explain later, you have to be careful here. Don't write too many instructions here. Sometimes, so here, this is very critical now to be very efficient. When you write the code here, you have to be very efficient. Why? Because if I go to once interrupt subroutine, and if I spend too much time here, this is gonna impact the other tasks. You understand what I'm saying? Any questions so far? So after I teach interrupts, now your program is not gonna, number one, your program is not gonna have only one test, but usually you are gonna have more than one test. You are running all of them at the same time. Don't be confused. In the last lab, yes, in the last lab you did 3 tasks, but they are not at the same time. You just selected to run one task at a time, right? Big difference. But here you can run 3 tasks at the same time, right? So, but again, it's somehow misleading. Because why somehow misleading? Because actually microcontroller can only execute one instruction at a time. Is that okay? But if I can jump quickly, from here to here, from here to here, you are gonna feel like you are running all the tasks at the same time. Flashing, you can see flashing. Buzzer is working. LCD is working. Everything is working perfectly at the same time. But in reality, only we run one task at a time. In reality, right? But because I do it very quickly, you are gonna feel like we are doing several tasks at the same time. Okay. So anyway, so today I'm going to give you more details. I finished. Hopefully you understand the all what I need from you here, guys, to understand the concept itself. You understand we are calling interrupt subroutine, but you are not calling it by yourself. There is an event should having to do that. You should understand why interrupts are really can make big programs simply because we use some kind of external circuit. For example, RTI timer. If you have a timer, this timer is external circuit. This one should help with the CPU. Again, we're not doing magic, guys. We're not doing magic. I want to count for a time. I want to make a delay. And instead of doing it's a delay by the CPU, I'm going to have external circuit. This external circuit can count for the delay. That's it. So that the CPU can be free to take care of other tasks. That's it. You got what I'm saying? So same thing when we have like serial communication. So we have external circuit. Same thing when you have a timer. You have external circuits that can do a part of the work. So CPU is not going to do everything by itself. So we have some external circuits that can do part of the work. Okay, because of these external circuits, we can make big applications. And that's what I told you in the first lectures. In the very beginning of this semester, I told you we have a microcontroller. Inside the microcontroller, it's a complete system. Inside the microcontroller, we have microprocessor, we have timer system, we have analog to digital converter. So we have several things here inside the microcontroller, several systems. Okay. Anyway, so now I'm gonna start to talk about programming. Okay. So now very clear. Our program will be something like that, guys. In our program, you have to do from now on, or when you use interrupts, your program is not going to be written in one place anymore. Your program is not going to be written in one place anymore. What do you mean by one place anymore? I mean this one, because that's what we have been doing from the beginning of the semester. From the beginning of the semester, we just write our program here. After I teach interrupts, your program, one task will be here. You have to write something here in the interrupts, another task here, another task here, another task. That's why your program is not going to be written in one place anymore, but in several places, as you will see. So now I want to teach how can you program interrupts. Okay, I'm going to start it here. First of all, I want to classify interrupts. We have 2 types of interrupts. We have one type we call it maskable, and we have another type we call it non-maskable. Okay, so again, I told you guys for interrupts we have many sources of interrupts, around maybe more than 20. So in the table here we have this table and this table here. Okay, so we have many sources of interrupts. Okay, here I'm gonna classify these sources into maskable and non-maskable. So tell us what you mean by maskable and what do you mean by non-maskable. Okay, so first, the English name maskable means what it means here. What do you mean by maskable as an English name? Here it means you can disable. Okay, you can disable this interrupt. This one is non-maskable. That means you cannot disable it. So we have two types of interrupts. One type of interrupt you can disable. You can turn off. Right? The other source you cannot disable. So what do you mean by when you disable interrupt? Okay, very important to understand this one. Number one, if you have interrupt source is enabled, what it means? If an interrupt source, for example, here I give you example of IRQ as an example. Okay, IRQ is enabled. What it means? Very simple. It means we have an external pin here. Every time there is a falling edge, I'm going to execute a subroutine. That's it. That's the meaning of enabled. Every time you request interrupt, when you raise your hand to ask a question, okay, because I enable interrupts, so I'm going to respond to you. I'm going to serve you. That's the meaning of it. However, if it is disabled, so if you try to interrupt me, I'm going to ignore you. That's the meaning of it. Okay. So if the interrupt is disabled, what it means if it is disabled? It means even if there is an event, even if you request an interrupt, I'm going to ignore you. What it means, ignore you, means I'm not going to execute the subroutine. Okay, guys? Is there any questions? Okay. So what I'm saying here, guys, we have two types of interrupts. One type of interrupt, we call it maskable. Maskable means I can turn it off, or it means even if you request to interrupt, even if there is an event, I'm not going to serve. Serve here means I'm not going to execute the subroutine. Okay. The other one is non-maskable. You cannot turn it off. You can't. It's always has to be on all the time. Okay. Actually, we have very few interrupts are non-maskable. Very few. And these interrupts are not general purpose. They are used for a specific purpose, like reset. Reset is non-maskable interrupt. That's why I'm going to only focus on maskable interrupts, okay? Because that's what we are going to do all the time. Because non-maskable are very few and they used for a specific, they are not general purpose, so you are not going to need them, okay? So, so here, that's why I'm going to focus on maskable interrupts. I hope, before I continue, I hope you should understand, number one, we have multiple sources of interrupts. Every source can request the interrupt. And you should understand what I mean by we serve request. You have to be familiar with these terms. Request, interrupt. You have to be familiar with serve as an interrupt. You have to be familiar if I enable interrupt, what it means. If I disable, what it means. If you disable interrupt, actually, that means I'm not gonna serve you. So even if you request, I'm just gonna just ignore you. I'm not gonna execute the subroutine. Is that okay, guys? Any questions? Okay. So now, so this is the first topic I want to talk about. Yeah. So you told us we have multiple sources interrupt. So please tell us how I can enable or disable interrupts. How I can do that. Okay, I'm gonna tell you how. Actually, we have two levels. One level we call it global masking capability, and the other one is local. It's like you have two switches. You have a master switch and you have local switch. Master switch, that means this is a switch for all interrupts. That's a master switch. Also, we have a local for each source. So let's talk first about the global. The global, if you remember CCR. In the CCR, I already explained the C flag, V flag, Z flag, N flag. I already explained all these flags. Today, I'm going to explain I flag. I flag means interrupt flag. This is a global switch. This switch can turn everybody off, but it cannot turn everybody on. It can, as I'm going to elaborate now. Okay. So this one here, guys. If you want to disable all interrupts, you have to put here one. So if you put one here, guys, regardless of the local switch, ignore the local switch. This is a master key. So here, if you put, very simple, look what I'm saying. If you put one here, you disable all interrupts. Very simple. Okay. So if you put one, how can you put one here? You can use this one, set E, set I, or you can use OR operation to put here one. So you can use this instruction or this instruction in order to disable all interrupts. I'm not going to look at the local. Okay, this is the master key. You disable all of them. Again, if you put here one, you disable all of them. Okay. Number two, if you put here zero, that doesn't mean all interrupts are enabled. No, all of them are enabled provided that the local bit is enabled. So now I'm going to look at the local bits. What do you mean? I'm going to tell you what I mean. Again, we have different sources, multiple sources. Every source has one bit to enable or disable the interrupt of this source, right? So what I'm saying is that if you put here one, okay, so I'm not going to even look at these local bits. All of them are disabled if you put here one. However, if you put here zero, that means now I'm going to look at the local bit. If the local bit, if you one or zero, if you enable, so it's enabled. If you disable, it is disabled. You understand what I'm saying? So I'm going to look at the local switch or local bit only if you put zero. Is that okay? So let me say it in a different way. Number one, let me say it in a different way. Number one, if I want to disable all interrupts, just to put one here, is that enough? Yes, this one is enough. How can you put one here? One of these instructions. Is that clear, guys? Now, number two, if I want to enable an interrupt, what should I do? Number one, you have to put zero here. This one is enough? No, is not enough. Okay, what else I have to do? Every source has a bit. When I teach every interrupt source, I'm going to tell you this is the bit for enable. If I forget, tell me what is the enable bit. Every source there should be one bit, enable bit, right? This enable bit. So if you put here zero, so an interrupt source is enabled if the enable bit is enabled using 0 or 1. So we're going to use 0 or 1 here. Okay. So for example, I don't remember, but we'll see later. But for example, 0 may be disabled. Okay. So if this one is 0, disabled. If this one is 1, is enabled. Okay, guys. So I tried to visualize it this way. So that's why, look here, guys. It's like if I wanna request. So imagine this is the local switch I told you. It's not a mechanical switch, guys. It's just one bit. It's a bit. Okay. So here, and we have different interrupt sources here. Okay. So if I want to enable this source, so I have to close the circuit here. That means I have to enable this local bit so that to close this one. And these switches are all of them connect or disconnect using the I bit. Okay. That means if the I bit is 0, so that means all of them are connected this way. So now it depends on the local bits. Okay. If you turn it, if you open it, that means you just disable these interrupts. If you connect it, you enable the interrupts. However, if you put here, if you close, if you open all of them this way, so regardless of what you are doing here, it doesn't matter. All of them are disabled. Okay, guys. Conclusion. Number one, guys, I hope you understand. Number one, what is the meaning when I say you enable interrupt source or you disable interrupt source? What is the meaning of that? If anybody doesn't understand it, please raise your hand. This is one thing. The second thing, you should understand I bit. If I put an I bit 1, that means all interrupts are disabled, right? However, if I put 0 in I, so now every interrupt source has a bit. Every interrupt source has a bit, and you call it local enable bit. Okay, so this local enable bit can decide if this one is enabled or disabled. Any questions? Someone can ask me, okay, everything looks nice, it looks easy. However, why sometimes I need to disable interrupt? Why sometimes I need something like that? Yes. That's true. keep in mind, as I explained to you before, every interrupt source is doing a task, a certain task. What if I don't want this task anymore? Okay, for example, I'm going to use RTI. I'm going to use it to make flashing LED. Okay, or I'm going to use RTI to make alarm sound. Okay, for example, now there is no alarm, and I want to turn the alarm off. Okay, the test, as long as RTI is enabled, you are going to hear a sound because this test is done by RTI. If you don't want to hear the sound anymore, all what you have to do just disable RTI, right? So the answer is very simple. Every interrupt task is doing a task. If every interrupt source is doing a task. If you don't need this task anymore, just disable it. When you disable it, you are not going to have this task anymore. Any question, guys? Okay, so now I finished this part. Now I'm expecting you know what I mean by enable interrupt, disable interrupt. Also, I'm expecting to know how can you do it. For sure, I didn't explain yet. For every interrupt source, I have to tell you where is the enable bit. You need to ask me. If I forget, you need to tell me. Every interrupt source, there should have one bit. This bit is enable bit, right? To enable local enable bit. Is that okay? So I'm gonna teach it when I teach every interrupt source. Any questions? Okay. The other thing I want to explain here, we have also another thing we call interrupt flag bit. So now you should know local enable bit. So for every interrupt source, I have to tell you where is the local enable bit. This one is used to enable or disable the local this interrupt source. Same thing for every interrupt source, I have to tell you where is the interrupt flag bit. So what is this? It looks like it's a bit. Yes, it's only one bit. But what is this? How it is useful? How I'm going to use it in programming? How this one is? I'm going to tell you. Okay. Look at the idea. How if this device, we have different devices here. We have different interrupt sources like RTI, analog to digital, timer system, RTI. We have different interrupt sources. Okay. If this interrupt source, if one interrupt source wanna interrupt the microcontroller, okay, it's gonna if you wanna request interrupt, how this can be done? It's like it's a communication language between the hardware. Hardware wanna talk to each other. Communication language. You understand what I'm saying? So how something like that should be done? Actually, for every interrupt bit we have, for every interrupt source we have one bit. This bit we call interrupt flag bit. If this device wanna request interrupt, all what you have to do just to put one here, and I will understand when you put one here that means you are requesting interrupt. You know this is similar to what? Okay, I'm teaching a lecture right now. Okay, you wanna interrupt me, okay, or you wanna interrupt me, what would you do? Okay. No, if you want to interrupt me, what you do, you have to raise your hand, right? You have to raise your hand to interrupt me. So once I see your hand raised, so that means you want to interrupt me. It's exactly the same thing here. It's exactly the same thing, right? So again, this is how the device. This is the hand of the device. So this is how the device is going to request interrupt. So if this device want to request interrupt, there is a bit. The device has to put one here in this bit. Is that okay, guys? That's what we call interrupt flag bit. This is how the story starts, or this is how the interrupt request is done. Okay, so if you can see here 0, that means there is no, you are not requesting interrupt. If I see 1, that means yes, you are requesting interrupt. Okay, guys. So now, very simple. Any interrupt source, if the interrupt source wanna request interrupt, simply the interrupt source has to write one here in what we call interrupt flag bit. Every source has an interrupt flag bit. This is the second one. So when I teach every interrupt source, I have to tell you where is the enable bit, where is the interrupt flag bit. Okay. So here the device has to put one here. Okay. Then what? Then after I serve the interrupt, after the microprocessor serves the interrupt, the microprocessor has to go here, put 0. So where you have to put this one? In the interrupt subroutine. So this is how the story is. The story starts this way. If this device wants to request interrupt, it has to put 1 here. Okay? And then once I serve this interrupt, once I go to the interrupt subroutine, you have to write a command here. You have to write a command here in order to clear this one. This is your responsibility. It's not your responsibility to put 1 here. This is the responsibility of the hardware. But you as a programmer, you have to write a command here in the interrupt subroutine to clear it. Why you want to clear it? Because I already served it. Okay? This is how we can communicate together. This is our language. You got it, guys? So again, very simple. If an interrupt source is requesting interrupt, the interrupt source automatically is gonna put 1 here, automatically. Okay. And then you are gonna execute a subroutine, interrupt subroutine. Here in the interrupt subroutine, you have to write a command to clear it, to put 0. Why 0? Because I already served it. Any questions? What happens if you forget to write this instruction? What happens? And it happened before, and it happens again. I'm sure some of you are going to make this mistake. What happens? So the device is going to put here 1 here to request interrupt. I serve the interrupt, but I forget to clear it. Can you think what would happen in this case? Guys, think about it. What can happen here? I'm going to have infinite interrupts. Because once what's going to happen is that when this is the main program, I go serve the interrupt, and then I'm going to come back, and then I find still 1. I'm going to think this is a new request. So I'm going to go again, serve, and come back. Still 1. I'm going to go and come back, So I'm going to have infinite interrupts. Your program will be frozen. Because you are going to only do 1 task. You're not going to do the other tasks. You understand that, guys? So what you have to do in programming, number one, the device is going to put 1 here to request interrupt. In the interrupt subroutine, you have to write a command to clear it, to put 0, because you already served it. So that after you put 0, maybe in the future, if there is a new request, this one is going to put 1. That's how it works all the time. This one has to put 1. I'm going to serve, I'm going to put 0. This one is going to put 1 to request interrupt. I'm going to serve, I'm going to put 0. And so on. That's how it works all the time. You got what I'm saying? But if I forget to put 0, this one is going to be 1 all the time. So it's going to be continuous interrupts. Because every time there is an interrupt there, every time there is a 1 there, that means you are requesting interrupt. So I'm going to execute a subroutine. It's going to be infinite requests. Okay, so for sure your program will be stolen, because all the time I'm going to execute the interrupt subroutine. I'm not gonna take care of the main program and the other interrupt subroutines. Any questions? Okay, so now let me summarize what I said, guys. Programming, if you want to program any interrupt subroutine, the first thing you have to do, guys, this number 1. I have to put 0 here. Just number 1. Number two, the enable bit, the local enable bit. The local bit. For every source, I'm going to tell you what is the enable bit. This number 2. For the enable bit, you have to enable the interrupt of this source. This number 2, right? Number three, make sure in the interrupt subroutine, you have to write a command to clear the interrupt flag bit. And every source has its own interrupt flag bit. I have to tell you where it is, in which register. I'm going to tell you. Is that okay? At least three things you have to do right now to program interrupts. Okay. By the way, your programming interrupts is very easy. Why it is very easy? Because it's copy paste. Usually the instruction you are going to use, it's like configuration. You remember when you configure port B, every time you want to use the LEDs, there are certain instructions you have to use this instruction all the time. It's the same thing. If you just know how to program RTI or IRQ one time, it's almost copy and paste. You are gonna just change those very small changes. Okay, it changes. So that's why programming it very easy. All what you have to do inside the interrupt subroutine. Here, if you want to do different things, you can just change the command, whatever written here. So if you want to do a certain task, you can write it here what you want to do, or you can change it, but the configuration will be almost the same. Any question, guys? Great. Okay, now I'm gonna come to a next point here. Okay, in the next point, so I told you guys, every time there is a interrupt request, and this interrupt request is coming from an event, as I told you, starts from an event. We have an event, so you have to make a request. If there is an event, you have to make a request. How can you make a request? From the flag bit, as I told you, you have to put one in the flag bit. At this time, once you put one in the flag bit, that means you are requesting interrupt. You raise your hand. You are requesting interrupt. Okay. Now, if I decide to serve this interrupt, I'm gonna go execute a subroutine and then come back. Okay. So the question is now the other issue I wanted, the other topic or the other issue I want to teach right now is I have to go execute a subroutine and come back. So the question is, where is this subroutine? Where is in memory? Which location is the memory? What I'm saying? You have to tell me. It's not something I'm gonna guess. You have to tell me. Is that like fixed location? So for this source, you have to put the subroutine in this location. For this source, it has to be in this location. Is that something fixed, or I have flexibility? I can put these subroutines anywhere in the memory. The answer is number one. Again, don't think we don't have only one source. We have multiple sources. Number one, you can put it, you have freedom. We have flexibility. You can put the subroutines anywhere in the memory. It's up to you. Okay, so for example, if this is a memory for just any number in location 5000, I'm gonna put the subroutine for IRQ starting from 5000. That's okay. And then for RTI, I decided for some reason I want to go for RTI at 7000. That's okay. That's okay. It's up to you. This is your manage it as you want. Put it anywhere. But now the problem is how the microcontroller can know. How the microcontroller can know in that IRQ is at 5000. RTI is at 7000 because these are not fixed. Maybe someone is going to select 5000 here, someone can select 6000. It's up to you, right? So it's up to you. So how microcontroller can know the location? So number one, we agree, guys. For the interrupt subroutine, we agree you can put it anywhere. It's up to you. However, you have to tell the microcontroller where is the subroutine. How can we do that? I'm going to tell you how. Simply, we have fixed location for the addresses. Say it again. I'm going to tell you. For example, for IRQ, so number one, you can put it anywhere. However, this address, you have to put it here in this fixed location, in this address. So what I'm going to do, guys, every interrupt source has 2 bytes. Fixed. Location is fixed, right? So you can put for every source, you can put the interrupt subroutine anywhere, but just please, you have to put the beginning address in this location. So that when I receive interrupt from IRQ, I'm going to go to this fixed location. I'm going to see what address is there, and then I'm going to go execute from there. You got what I'm saying? So that's exactly what happens. So every interrupt source, guys, it has two fixed location in the memory. You have to store this address in these 2 locations. So you can put it anywhere. And in programming, you have to write an instruction to store the beginning address here, so that the microcontroller can know. So where are these fixed locations? I'm going to tell you why. If you go to the table here, guys, you can see. Here you can see I jump by 2. You can see that that's what we call vector address. Also, you should be familiar with the term vector address. So vector address, that means this is the address of the fixed location. You have to store the beginning address of your subroutine in this location, so that the microcontroller can know where is the beginning of your subroutine. Okay, guys. So here you can see we jump by 2. Why you jump by 2? Because this is 2 locations to store address. That means, guys, listen to me. For IRQ, if you want to use IRQ, so F2, so you store the beginning address in this location and next one. Is that okay? Fix it. This is fixed location. Same thing for any other interrupt source. If you want to use timer, it's channel 0, so you have to store the beginning address here. If you wanna use timer overflow, you have to store the beginning address here. That's what. So this address, we call it a vector address. Vector address. So vector address is a fixed address, predefined fixed address. This is where where I can tell the microcontroller what is the beginning of my my interrupt subroutine. So every interrupt source has a vector address here. These are fixed. Yes.
What's unimplemented instruction?
What is it? What is what? I don't know. I never used it. I don't know. Maybe if you are trying to run an instruction and this instruction does not exist, or this machine code does not exist, maybe so it's automatically it's gonna come here. So here you can make like error message, something like that. Maybe that's it. So here, guys, so here interrupt is the interrupt starting address. To serve an interrupt, the CPU needs to know the starting address of the interrupt subroutine. This address we call it, we have to store it in the interrupt vector. Okay. So here I give you example here. So we have here RTI. Okay, RTI. RTI interrupt subroutine. So here you have to put the beginning address. You have to store it here. So you can. This is an interrupt subroutine. You can put it anywhere, but just to give me the beginning address, you have to put it here in this location. This is in case of IRQ. Okay, but for so every source has a different addresses, as I explained. Any question, guys? So how can you do that, or how we will do that in the programs? We will do this way, as you will see later. So here, guys, number one, you have to say org, and then you have to put here the beginning address like FF2, and then you have to say dc.w, and then here you have to put the name of the subroutine, So this one has to be fixed. You can't change this one. However, this one I can change for sure, because this is the name of the subroutine. So if you call the subroutine IRQ ISR, you can just use this name. If you use a different name, just put it here. Okay, guys, any questions? So this is how we're going to do it in our program. So now our program is not going to have only two orgs as we did before. So what happened before, we had one org, 1000, and then we put all the data here. Let me go to empty slide. Okay, so what we did before, guys, we had org 1000, and then we put all data definitions here, and then we did org 4000, and then we did the program. The program was here. Now I'm gonna have, for every interrupt source, you have to say org, and then you have to say, for example, whatever the address, the interrupt, the vector address of this interrupt source, then dc.w, and then the name of the subroutine. So that when you write a subroutine, for example, I can say here IRQ_ISR, any name. But usually, because this is a subroutine for IRQ, I'm gonna call it IRQ. Because this interrupt subroutine, I'm gonna call it ISR. And then I'm gonna write here in my program, I'm gonna write this way, okay? And then this name, I have to put the name here, okay? Why? Remember, as I explained before, when you put the name here, this name is gonna be replaced by the address, right? So this name is gonna be replaced by the beginning address. By this way, I'm gonna store the beginning address in this location. Okay, guys? So that's what also I have to do in the programming, okay? Any questions? Okay. The last thing I want to talk about before the last thing I want to talk about, interrupt priority. What it means. I'm going to tell you what it means. Okay. Now, microcontroller, we agree microcontroller can execute only one instruction at a time. We agree on that. Okay. What happens if there are three interrupt requests coming from three sources at the same time? So as I am the microcontroller, I find that there is a request coming from IFTI, there is a request coming from IRQ, there is a request coming from timer overflow, for example. So I have three requests. Okay, I can't serve all of them at the same time. So I have to select. There should be some kind of priority. I have to select one of them. You got what I'm saying? So which one I have to select? Which one? That's what we call interrupt priority. So we have to make some kind of priority so that if I have multiple interrupt requests at the same time, I need to select the one that has the highest priority to serve it. Highest priority. Okay. So how can we do it? Okay, this is somehow a little bit different from one microcontroller to another, but the way we do this way, guys, as you see here. Number one, we have fixed priority, fixed priority. So as you see here, guys, whoever come here, you can see the priority is decreasing this way. So whoever comes here first in the table has higher priority. For example, so if I get interrupt from here, and interrupt from here, and interrupt from here, which one I have to serve? For sure, I have to select this one because this one has higher automatic priority. You got it, guys? Okay. So for another example, if I get this one and I got this one, which one I have to serve? This one, because this one has higher priority. Very simple, right? So as you see here in the table, whoever comes in the table first, guys, has higher priority. So if I have two interrupts at the same time, this one and this one, okay, so I'm going to select this one. If I have this one and this one, I'm going to select this one, and so on. Fixed priority. Okay, guys? Do you mean I have no control at all? I have no control at all on selecting, on managing the priority here? The answer is no. You have a control, but very limited control. By the way, other microcontrollers may have more control, but anyway, here you have a limited control. What do you mean by limited control? All what you can do, you can pick up only one. For example, I care too much about timer overflow. You can only take one and put this one on top of everybody. This is very limited control. After that, everything else will follow the rule I explained before. Whoever comes here in the table. So here I have a very limited control in the priority. You can only select one, put it on the top of everyone. Okay. After that, whoever comes first are going to be served here. So how can you do that? I'm going to tell you how can you do that, guys. All what you have to do, we have a register. This register is called high priority, HBRIO, high priority. All what you have to do, the source you want to put it highest priority, you have to select the code for this source and put it here in this register. What do you mean by the code? How I can get this code? I'm going to tell you how. So if you come here, the code is actually the least significant byte. The code is the least significant byte. Okay, guys? So for example, if I want this one to have the highest priority, so I'm going to put GE. So I'm going to say move byte, $, GE, and HBRIO, right? Is there O or not? Yeah, there is O. That's it. Only one. You can select one and put it on top of every one. Okay. I don't think in this class we're going to need something like that. Okay. But anyway. So, but also you need to ask me why sometimes I need to pick up one and give it highest priority. Okay. My answer to this question is it depends on the application. If you think you need for some, this interrupt is very time sensitive. Should not be delayed. You are counting something, you are measuring something. You understand what I'm saying? Because listen to me. If I have 3 interrupts at the same time, I'm going to serve only one at a time, right? So that means two interrupts should be delayed. Delayed means when you request interrupt, you may not get immediate service. You may not get immediate service. It's going to be delayed. So what I'm saying is that it depends on the application. Maybe if you do flashing. If the flashing is delayed 10 nanoseconds, it's not a big deal. 1 microsecond is not a big deal. I want to make flashing every 1 second. 1 microsecond is not a big deal. So it doesn't make sense to give this one very highest priority. You know what I'm saying? But if I have something like very sensitive, time sensitive, I need to set it very quickly. Okay. For example, I have pulses. These pulses are, for example, events or pulses. These pulses have very high frequency, and I need to serve every pulse quickly. Otherwise, if I don't do that, maybe I'm gonna miss one pulse. You understand what I'm saying? For example, let me explain what I mean so that you can understand better. So what I'm saying here, guys, I'm just Just you can think, you may not need it. You may not need to set the interrupt. You may not need it. Also, you may need it, right? So what I'm saying is that, look here, guys. For example, there is IRQ here. We have here pulses coming this way. And I want to, for example, count. Every time there is a falling edge, I want to count. So this is number 1, this is number 2, number 3, and so on. Okay. So higher the frequency. If the frequency is high, that means I have a very short time to finish serving the interrupt, because what happens is that once you request interrupt here, I have to serve this interrupt before this one comes. You got what I'm saying? What happens if you don't do that? What happens if I don't do that? What is going to happen is that this one and this one, both of them are going to be counted like one interrupt, not two. You got what I'm saying? So if you request interrupt here, but I'm going to serve you, for example, here, for example, that means these two are going to be counted as one, not two, because delay. Anyway, if you have something sensitive like this one, high frequency, it can come with very high frequency this way, and you don't want to miss the event. So in this case, I can say yes, you can make the IRQ has the highest priority. Any question, guys? You understand the story of the priority. You understand number one, the idea of the fixed priority. Fixed priority means whoever comes here first has highest priority. So this one has higher priority than this one, automatically. Is that okay, guys? However, you have little control. I can pick up one, I can put it on top. That's it, only one. Little control. Other microcontroller, maybe they have more control, but this one has little control. Any questions? Okay. So now, before I give you details, guys, so now at least here I'm talking about programming. If you want to program microcontroller, if you want to program interrupt, what should you do? Number one, you have to do this one, CLI, number one. Number two is the enable bit. You have to take care of the enable bit. This is number two. Number three, you have to write an instruction to clear the flag bit. That's number three. Number four, you have to write an instruction like this one to set the ISR starting address. You have to tell microcontroller what is the beginning address. This is four things you have to do. Number five, which may or may not need, it's not necessary. This one, the interrupt flag, if you need. But if you don't need, okay. So most of the time we're not gonna write it, most of the time. But just in case you need it, you can. If you don't, this one is optional. You may not need it. Okay. So now I wanna tell you the whole story before I move forward. So this is like the complete story of the interrupt cycle, interrupt service cycle. Let's see how this cycle works. I'm gonna read it one by one. Let's see how it works. Okay. So the interrupt service cycle, guys, is gonna start with an event. That's for sure. The beginning of the story, there should be an event. That's number one. And because of this event, the device that you have to put one in the flag, in the interrupt flag bit. Okay. So that the hardware can know that you are requesting interrupt. This is number one. So the beginning of the interrupt service cycle, number one, an event. And the hardware is gonna put one in the interrupt flag bit. This is similar when you raise your hand, right? Event is like you have a question. So you have a question, this is the event. And then you're going to raise your hand. You got two things. Event, you have a question you need to ask me. And then you need to raise your hand. So raising your hand, you have to put one in the flag bit. The question is the event, okay? This is number one. Number two, one of two things should happen. Either I'm going to serve this interrupt or I'm going to ignore this interrupt. One of two things should happen: ignore or serve. Okay. In order to serve the interrupt, two things should happen to serve. Otherwise, I'm going to ignore it. Number one, the interrupt has to be enabled. The interrupt is enabled if the I bit is enabled and also the local interrupt bit is enabled. If both of them are enabled, that means the interrupt is enabled. This is number one. Number two, this interrupt should be the only interrupt or this one has the highest priority. If these two conditions are true, I'm gonna make the decision to serve this interrupt. Okay, guys. So in order to serve the interrupt, number one, it has to be enabled, and enable means two things. The I interrupt and the local interrupt bit should be enabled. Number two, this interrupt it should be the only interrupt, or this one has the higher priority. So if these two conditions are true, okay. So now I'm gonna start serving you. So now here I'm gonna say how can you serve the interrupt. Any questions so far? So if I decide to serve interrupt, what should be done? Number one, to serve so from here serving interrupt. Number one, all the registers, 9 bytes, all the registers are pushed to the stack automatically. You don't need to do anything. This is done by the hardware. You don't need to do anything. So number one, to serve an interrupt, all the registers are pushed to the stack automatically. All of them, right? CCR, A, B, X, Y, B, C. All of them are pushed to the stack automatically. Is that okay, guys? Okay. And this is different from jump subroutine. If you remember, when you call a subroutine and you use jump subroutine, what pushed to the stack is only this one, the return address. Do you remember? Only the return address. So jump subroutine is going to only push the return address. But here in the interrupt, automatically, all the registers are pushed to the stack, all of them. Okay, this number one. Number two. Any questions? Also, CPU is gonna prevent further interrupts by disabling I. I is disabled. I is disabled. So also this is done automatically. You don't need to do anything. This one is done automatically. Why? Because nested interrupts are not allowed. Oh, what do you mean by nested interrupted? I'm gonna tell you what I mean. Look here, guys. This is the main program. We have here one interrupt, right? So from the main program, there is an interrupt. I'm gonna go to this interrupt. What happens if there is another interrupt here? If interrupt here coming from another source, should I jump from here to go to the another similar to in function call a function? Is that something allowed? No, it's not recommended, because usually this makes like the system has low performance. Usually, if you so what I'm saying is that's why automatically you don't need to do anything. It's automatically. Once I serve this interrupt, I'm gonna disable I. So that I'm not gonna allow more interrupts. That's why nested interrupts are not allowed. After I finish, I'm gonna enable I again, because nested interrupts are not allowed. Automatically, you don't need to do anything about it. By the way, you can cancel it if you want. As far as I know, it's not recommended to do that, because the performance of the system is not going to be good. But you can cancel it. Simply, once I come here, I can write here, I can write CLI here. I can write here CLI to enable interrupts, so that I'm going to enable nested interrupts if you want to make it. But anyway, this is not something recommended anyway. But you should understand, interrupts are disabled automatically. You don't need to do anything, right? Because the system is not going to allow nested interrupts. But for some reason, if you want to do it, you can do it, but you have to write the instruction here to enable interrupts. Yes, you have question?
Isn't stack
Stack here?
Yeah, by recursive program. So that will be less than one.
Sorry, say that again?
Or recursive program that calls itself.
But where here we have a recursive program, how can you say the recursive? What is the function that's going to call itself?
We can have our subroutine call itself.
Yes.
To do something.
Interrupt subroutine call itself.
Yes.
But we don't call interrupt subroutines. We don't call them. The calling is coming from event. I'm not going to write an instruction to call it.
Then we could have an event and some X conditions. And otherwise,
I don't know. You can do it whatever you want to do it. But anyway, as far as I know, it's not recommended to make nested interrupts. You got what I'm saying? It's not recommended. So you have to be careful here. That means you should not enable interrupts here. What's going to happen automatically once I call a subroutine, automatically all interrupts are going to be disabled. I is disabled, and when I leave, before I leave, all of them are enabled again. Okay. So even if another interrupt has, even if this interrupt has more priorities than this one, yes, we don't care. We only care about priority when I select, at the point when I select. Now I want to serve interrupt. So which one I have to serve right now? But once I decide to serve one interrupt, so I don't care now about priority. So I'm not going to leave this one because this one has more priority. No, nested interrupts are not allowed. Only after I finish and come back, now I'm going to see how many interrupts I have and which one have more priority. You understand what I'm saying? Any questions? Okay. So what I'm saying here, guys, this is done automatically. All interrupts are disabled automatically. Okay. Number two, in the after that, guys, microcontroller now it has to go to the interrupt subroutine. The next point here, it has to move to the interrupt subroutine. How it has to move to the interrupt subroutine? It needs the beginning address. So microcontroller has to get the beginning address from. It has to resolve the interrupt vector. I have to get the beginning address. How we get the beginning address? From this location. If this interrupt is for example, is coming, if this interrupt is coming from IRQ, so I'm going to read the beginning address from here. If this interrupt is coming from timer 4, so I'm going to read the beginning address from here. Okay. So, and then after that, I'm going to jump to the subroutine. We are going to jump to the subroutine here. Don't forget, you have to cancel the interrupt request here. So you have to write an instruction here to cancel the interrupt. You will regret if you forget to this one. You will regret because your program is going to be frozen and you may spend hours to look for where is this mistake. Sometimes very, very small mistakes waste too much time. So you have to be smart. You have to be efficient here. Okay. So don't forget to write here the interrupt subroutine to cancel the interrupt subroutine. Okay. After that, then we are going to execute the interrupt subroutine, and then at the end of the interrupt subroutine, we have an instruction, we call it RTI. This is the last instruction here in any subroutine, RTI. Remember, before for any function we have RTS. Now we have RTI. How they are similar and how they are different. I'm going to tell you very simple. RTS used to pull only the return address 2 bytes from the stack. Okay. However, this one RTI, it has to pull 9 bytes. Everything here, 9 bytes from the stack. You got what I'm saying? This is the difference between RTS and RTI. RTS is gonna pull only the return address. RTI is gonna pull everything back. Okay. And because you are gonna pull everything back, so you know what I did right now? Listen to me, very important. I'm gonna push all the registers and then I'm gonna pull all of them back. You know what I did right now? This one similar to what I taught before when I told you if you have a function, usually, you remember when I taught it before, I told you for any function, it's a very good practice for any function to push, and then you pull. So any register you want to use here, you have to save it and get it back. That's exactly what happened. But you don't do it by yourself. It happened automatically. You got the idea? So here, what we did before, any register I want to use, we used to push it. And then I'm going to pull it back so that there is no interference between the subroutine and the main program. Is that okay? You have to do it by yourself. But now the same thing happened, but automatically. All the registers are gonna nine bytes are gonna be pushed. All of them are gonna come back. Any questions? Any question, guys? So now, very important thing. If you have a return value, if you want to return some value from the interrupt subroutine, can I use because this is going to be also one of the common mistakes. can I use one of the register to return a value in this register? So for example, I'm going to do the interrupt subroutine. I want to count something. So for example, I'm going to use register A as a counter. I want to count how many interrupts I have. So every time it's interrupted, I'm going to say increment register A. Every time I want to count how many interrupts. So every interrupt, I'm going to say increment A, increment A, increment A, increment A to count how many interrupts. Can something like that work? The answer is no. It's not going to work. Why? Because always register A is going to take the initial value back. Because very serious, very important. You can do something like that. The return if you have a function, as I thought before, function is okay. But for the interrupt subroutine, it's not okay. Why? Because you have no control. All the registers are going to be pushed. All the registers are going to be returned back. So all the registers are going to take their initial values back. So whatever you put in A, this one we're not going to retain it. It's not going to be retained because they are going to get the original. So if you want to return something, it has to be a memory location. So it has to be in a memory location. Any question, guys? Okay. So before I move forward, so I'm going to go through again these steps, because these two slides are actually summarize everything I explained in interrupt so far. So let me go through it, guys. Number one, interrupt service cycle. It starts when an event occurs. And because of this event, the interrupt source has to request the interrupt by putting one in the interrupt flag register. Once you put one in the interrupt flag register, that microcontroller can know that you are requesting interrupt. Similar, when you raise your hand, I can know that you are interrupting me, right? So this number one. Number two, now I have to make the decision, either serve, but wait, I'm going to make the decision after I finish the current instruction. And now I'm executing an instruction. I'm not going to suspend the instruction I'm executing right now because there is an interrupt. No, I'm going to check for interrupt after I execute the instruction. So after I execute the instruction, the hardware is going to check for interrupts. Now we have to make a decision, either serve or ignore. Okay, I'm going to serve if the two conditions are true. The first condition, I is enabled, local enable bit is enabled. That's number one. Number two, if this interrupt is the only interrupt or this interrupt has the highest priority interrupt. So if these conditions are true, now I'm going to serve this interrupt. And here, starting from here, I'm going to serve this interrupt. How you are going to serve the interrupt? Number one, automatically, all the registers are going to go to stack, push to the stack automatically. You don't need to do anything. Just everything is going to be pushed to the stack. This is number one. Number two, the CPU is gonna disable I. Why? Because nested interrupts are not enabled automatically. You don't need to do anything. That's number two. Number three, CPU is gonna go to the vector, interrupt vector, to get the beginning address, and put it in BC. So it has to get the beginning address. It has to put in BC so that you go to this location to serve the interrupt. Okay. Then inside here, inside the interrupt subroutine, it's this one is not automatically. This is something you have to do it by yourself. You have to write here an instruction in the interrupt subroutine to clear the flag bit, right? And then I'm going to execute the interrupt subroutine until I found RTI. The last instruction has to be return, or RTI, return interrupt. RTI, number one, it should retrieve all the register again, should pull all of them from the stack, and then it has to enable I bit again, and then we're going to return the main program again. Any question? So now you can use in any interrupt subroutine, you can use all the register without any fear of interfering with the main program. Understand what I'm saying? Because I'm using a value in register A. In the main program, A has a certain value. If interrupt happens, you are going to damage A. You are going to make a mess. Your program is not going to work this way. That's why automatically when there is interrupt, automatically the hardware is going to take care of it. It's going to save this value. Okay. So that means inside any interrupt subroutine, you can use all the registers. You don't need to push anything similar to what we did before. You don't need to push anything. Okay, to save then this is going to be done automatically. So you can use all the registers without a fear that this is going to interfere with the main program. Any questions? Okay. Now the good thing is, look here, guys. Programming, believe me, it's very easy. Once you know how to program one, all of them the same. Okay. So here in this slide, I summarize. Here I summarize in order to program interrupt, you have to do these steps. Okay, and I would be more specific when I talk about every interrupt source. I'm going to be more specific. Now it's just in general. Number one, you have to initialize the interrupt vector as we agreed. The interrupt vector. This is, you have to do it. Org, you have to use org. You have to see what address you have to do here, dc.w, and then you have to put the name of the subroutine. You have to do this one. Okay, that's what you have to do in the main program. Okay. Number two, you have to write some instruction to do configuration. And this configuration may be different from one source to another. For example, if I want to configure the timer, if you have a timer and I want to do configuration to the timer, so in this case, the configuration is the timeout. I have to write a command to do this configuration. I have to tell the timer, please timer, trigger interrupts every 1 millisecond or every 2 milliseconds and so on. So you have to do this kind of configuration, right? So this configuration is different. This also should be done in the main program. This one is different from one source to another. For example, in case of IRQ, you can have interrupt when it is a falling edge, or you can have interrupt when it is low level, zero level. So zero level, or you have the choice. It's up to you. And later when I explain the input capture, we have more option. You can trigger interrupt when it is falling, when it is rising, when it is both falling or rising, right? So you have different options. So you need to select. That's what we do here in configuration. So every interrupt source has different configuration, right? And you have to write commands to configure it. Yes.
How does it perform mechanic when you give both rising and fall?
Mechanically. I don't know what you do mechanically.
How is it that flip-flops are able to accept both rising and falling? Do we have?
It depends on what you wanna do. Do you wanna interrupt this when there are rising only, or you wanna capture, or we need interrupts when there are falling only, or you need interrupts when both rising or falling? It depends on the application. It depends on what you wanna do. Just you need to tell the hardware what you wanna do, right? So you have to do. That's what I'm saying. But that's what I'm saying. Configuration. So you have to write a certain value, as I'm going to explain later, in a certain register to tell the hardware, I want to use the IRQ this way. I want to use the timer this way. You got what I'm saying? Anyway, I'm going to give you more details. But for now, I just want to summarize how can we program it. So you have to write this one. You have to write some instruction for this one. You have to write some instruction, guys, as I explained, for the global. For the global, I told you have to write CLI. For the local, if there is a local bit, you have to enable the local bit. For every source, I'm going to tell you where is this local bit, in which register, where it is. Okay. So this is what you have to do in the main program. Now, what should you do in the interrupt subroutine? Number one, as I told you, you have to clear the interrupt flag bit. Don't forget it, please. Don't forget it, because you have to clear the interrupt flag bit. Okay, because you already served the interrupt, right? This is so it's similar. So you're gonna putting down the hand of the device. Okay, okay. Now I serve it you. So put your hand down. I already serve it you. Okay. Now if you need more interrupt, you just raise your hand. I'm totally fine. But for this interrupt is done, just put your hand down. So I have to write an instruction to do that. And then at the very end, I have to use RTI. Okay. So this is in general, for any interrupt source, for any interrupt, we have to do these ones. Now I'm gonna go more specific right now. So now I'm gonna take source by source, and every source you will see I'm gonna do these steps. Okay. So now let's start with the first one, IRQ. Any questions? Okay, easy. You see it right now. So number one, I'm going to teach IRQ. So what is IRQ? As I told you, IRQ, we have a pin, external pin. And this external pin is connected to a sensor, a device connected to somewhere, okay? And then every time there is a falling edge or zero level, you can trigger interrupt. This is something you can select. It's up to you. If you want to go for falling edge, yes, you can just select falling edge. If you want to go for low level, you can do that as well, okay? So you have these two options. External pin. So number one, where is the external pin? If the external pin is here, look here, guys. PE1, the second one here. Okay. So the falling edge has to be at this pin, and that's what we are going to do in the coming lab. Okay. In the coming lab, we are gonna, if you want to trigger IRQ interrupts, you should have a wire here, and you have to generate. There should be a falling edge on this pin, the second one here. Okay, guys, this is IRQ. Any questions? So this is an external pin. Okay. Now I'm gonna come to this slide here. I'm gonna explain everyone in details, specific. Now, for any interrupt source, you told us I have to initialize the interrupt vector. That's true. So how I can do that for IRQ? Very simple. You have to use this one because this is the magic number for IRQ, fixed location. So you have to use this one, okay? And now you have interrupt subroutine. This interrupt subroutine has a name. You can use any name, but whatever name you are going to use, you have to put it here. Because this name is going to be replaced by the address, by the beginning address. In this case, I just selected IRQ underscore ISR. You can select any other name. So the subroutine here, this is the name of the subroutine I'm going to use. You can use any other name, but what's important is whatever the name here, it has to be the same name here. And the reason I put the name here, because this name is going to be replaced by the address. By this way, you are going to store this address in this location. Okay. I think that's enough for today. I'm going to continue next time. Okay, guys.